Hello, so today we're going to do a few exercises on magnetic field and a little bit of calculations on magnetic forces as well, good practice for in general review, and we'll look also a little bit at Faraday's law, a slightly different perspective that we've used in class. So first little exercise that we'll do is we're going to imagine that we have a sheet of current, an infinite sheet of current that is extending along the z direction. And there's, we're going to take the frame of reference X and Y vertical. And there's, so therefore, a sheet of current here, and we want to calculate what is the magnetic field created by that sheet of current in a place above the surface of the sheet of current. So that sheet of current is defined in terms of the current density, a linear current density. That we're going to call J. And J is going to be current density per unit of width of the sheet. So it's a lot easier to see in cross sections, and we'll be able to locate the point P where we want to calculate that magnetic field. So from a cross section perspective, here's that sheet of current. Here's the x-axis extending to the right, the y-axis extending vertically, and the z-axis in sticking out of the page, which is also the direction of the current density. So the current flows out of this sheet in infinite direction along the z-axis, which is again the axis perpendicular to the page, and we would like to calculate what is the magnetic field at a point P out here located above that distribution of current, and not necessarily straight above it. But it will be defined by a certain angle with respect to the two ends of the width of the sheet of current. We're going to have an angle theta 1 right there and an angle theta 2 right here. So every time we have continuous distribution, be it of charge or current, we know that we're going to have to take an infinitesimal amount of charge or current and be able to calculate from that infinitesimal what will be the magnetic field created at point P. And we can certainly do the same here. So we're going to take a small element, dx, here, in width, and we'll look at what is the magnetic field created by that element dx at point P. Well, the current is flowing this way. We can use the curl of the right-hand rule, the thumb directed in the direction of the current, and the curl of the right hand is going to give us the direction of the magnetic field at the location of point P. We know the B field has to be perpendicular to the, if you want to think of it, r hat, the direction towards the point of observation, as well as perpendicular to the line of current, infinitesimal narrow line of current. That's going to give me a dB pointing this way. Here's the dB magnetic field, infinitesimal magnetic field created by that infinitesimal thin line of current. And then we can apply, and this is, we can apply the Savart Law to this. And we know that this dB in magnitude is going to be equal to mu0 divided by 2 pi r, r being the distance of observation, times the element of current di. So fundamentally, this element of current di is going to be contains our variable of integration, and we'll be integrating over this width. So we have to express di as a function of this width, at least at the beginning. So we know that this di, element of current, is proportional to the current density, the linear current density, times the little width dx. So that's going to be my transition from a current variable to a position variable. So I'm going to have a dB, magnitude of the field at this point P, equals mu0 J divided by 2 pi r dx. Right. But notice that there's still a little bit of a problem, because we are given the position of P in terms of angle. We know nothing about this width. So we're going to have to work a little harder to get this expression in terms of an angle, so we'll be able to integrate over the angles. So here's what we have to do. First of all, I'm looking for the components of B. So might as well calculate these components of B right away. I have an angle theta right there, which describes the position of P. That means I find that same angle right here. Here's that same angle theta. So immediately I can calculate the dBx, the component of B along the x-axis. It's going to be the projection of B along this x-axis. So we're dealing now with a sine. It's going to be mu 0 j over 2 pi r dx sine theta. And then I have to take into consideration the fact that dBx, which is going to be this component, is oriented horizontally in the negative direction of my x-axis. So I have to introduce a negative sign to be consistent. And of course, we can also very similarly extract the dBy, the component of dB along the y-axis, and this is going to be simply mu 0 j over 2 pi r, here with a positive sign because it's directed in the positive direction of the y-axis. And now this is the cosine of the angle. So obviously we're going to have to relate dx to the angle. And that's where this problem is kind of interesting, and you'll see a lot of similarities in other type of problems in physics or even in engineering. It doesn't really matter. What I'm going to do is going to expand out this region so that we can see a little better. So I'm going to have this element dx here, and then point P located over there. So we're going to have an angle theta right there, and an angle theta plus d theta right here. So we are at the distance little r from point P, and this distance, which is not the same thing as r, is slightly different. This is going to be an r plus dr. So you might argue, well, this is a smaller distance that would make dr, it should normally be r minus dr. Well, it doesn't really matter, you'll see why anyway, but you can imagine that my dr is a negative value here, so fundamentally it doesn't really matter. The only thing that matters is to know that we have r and r dr corresponding to a theta and theta plus d theta. So I'm going to try to correlate that length dx to the angle theta and little r. And to do this, the easiest is to look at this little right angle triangle right here. So this right angle triangle, in this dx in this right angle triangle where I find my theta plus d theta right here. What do I have? I have, let me see, did I do it right there? Well, actually, I can also use, yeah, no, that works. So what do we have? We have, in terms of, I'm interested in this, that gives me dx projected on there, dx sine theta plus d theta is more or less equal to this length right here is the arc of length r corresponding to the angle d theta. So this is about the same thing as r d theta. Well, actually it is, I'm sorry, this is r. Well, we can use slightly different. No, that works as well. That works as well. So what do we have? We have sine theta plus d theta. We can neglect d theta with respect to theta. So this is going to be a dx sine theta is more or less equal to r d theta. And that's the linkage, the bridge between a dx integration and a d theta integration, the angle between the two variables are connected through this. There are different ways of looking at it. Again, you can also use this triangle to extract the information. It doesn't really matter, in fact, because we're dealing with infinitesimal changes in angles and positions, so that you have a little bit of flexibility right there. So if you take your dx, that gives me dx equals r over sine theta, d theta. And I can therefore replace into my two values of magnetic field. dBx is equal to negative mu 0 j over 2 pi r. dx is r over sine theta, and then times d theta. The same thing for dby, mu 0 j over 2 pi r over sine theta. And I'm missing the sine theta up here, sorry. And then I have another d theta cosine theta coming from here. So we see immediately that we have simplifications. R and R cancels out. Sine theta and sine theta cancels out. Here R and R cancels out. And here we have d theta cosine theta over sine theta. So these two values of the magnetic field can be written as, regrouping everything, dBx is equal to negative mu 0 j over 2 pi d theta, simply. And the other dby equals mu 0 j over 2 pi cosine theta d theta divided by sine theta. And now it's just a matter of integrating this over the angle varying between theta 2 and theta 1. So we can do that very readily. So the first equation bx becomes the integral of mu 0 j over 2 pi d theta. Well, I'm going to write it out. Negative mu 0 j divided by 2 pi. The integral of d theta between theta 1 and theta 2. Between theta 2 and theta 1. From small angle to large angle, scanning along the x-axis. And my by is going to be the same thing, mu 0 j over 2 pi. And the integral between theta 2 and theta 1 of cosine theta d theta, this is the same thing as d of sine theta, divided by sine theta. And immediately we see how we can integrate that very readily. We can remove this. And first expression gives me bx equals negative mu 0 j over 2 pi. And then the integral becomes simply theta 1 minus theta 2. And by, the integral d theta over sine theta is ln of sine theta. And taken between theta 1 and theta 2, mu 0 j over 2 pi, ln of sine theta 1 divided by sine theta 2. Here are the two expressions of the magnetic field at point P created by this sheet of current flowing along the z-axis. We have the two components. So what is fairly interesting is to look at what happens if I were to bring my point P as a special case right in on the axis of symmetry laterally with respect to the sheet of distribution, the sheet of current distribution. So we can do that, and we can redraw the situation to see what happens. So here's the distribution of current along the x-axis. The y-axis is the axis of symmetry of the distribution. And now I'm going to take point P at that location. So point P now is symmetrically located with respect to the two ends. I still have theta 2 right there, and my theta 1 measured from the x-axis becomes that, theta 1. And of course this angle, being symmetrical, is also theta 2. So we see immediately that we have theta 1 is pi minus theta 2. So we can introduce the inside the expression for bx, negative mu 0 j divided by 2 pi, theta 1 pi, minus theta 2 minus theta 2, minus 2 theta 2. And what happens for by? Well, we have mu 0 j over 2 pi, ln of sine theta 1, which is pi minus theta 2, divided by sine of sine of theta 2 by itself. Sine of pi minus theta 2 is the same thing as sine of theta 2 over sine of theta 2. The fraction is 1, which gives me an ln of 1 equals 0. We therefore find that in the situation where p is symmetrically located, we have a bx equals negative mu 0 j over 2 pi minus 2 theta 2, and by equals 0. So the magnetic field is fully contained within the horizontal plane, parallel to the x-axis, and the field being in this direction. Here's the magnetic field at point P above this charge distribution when you have P located symmetrically with respect to the lateral distribution. So what happens underneath? Well, if I were to put point P underneath that distribution, I would find, on the other end, I would find the same thing. Could redo the same calculation, or obviously through principle of symmetry, we expect the magnetic field B to be pointing this way. Notice what is really interesting is you have no dependence anymore on the position R. That dependence is kind of gone. So, what can we say further about this? Well, what is the magnetic field? Well, let's call this point Q. So B at point P is fundamentally equals to. Well, no, we don't even need to do this. Let's look at what happens. There's a better way to do this. What happens if that sheet of distribution becomes infinite in width? So in other words, I'm going to making this sheet infinite means that theta 2 is going to get smaller and smaller. As theta 2 gets smaller and smaller, I'm going to go theta 2 going towards 0. That's going to be an infinite sheet along the x-axis. If I go theta 2 equals 0, that means suddenly my Bx field simplifies to this expression, which is equal, therefore, to mu 0, 1/2 of mu 0 j. Very simple expression with a negative sign still there for the magnetic field at point P. At point Q, now we can get to point Q, so that will be at P. At Q, point Q, B will have the same value, but except in the negative direction, or in effect in the positive direction of the x-axis. So at point Q, it would be positive 1/2 of mu 0 j. So we see that if we were to plot the magnetic field B in this infinite sheet of distribution as a function of y. So here that would be point P corresponds to y being positive, and here that corresponds to y being negative. When y is a negative, the value of my B field is positive 1/2 of mu 0. It would be plotted here. Positive 1/2 of mu 0 rule j. And in the negative, in the positive part of the y-axis, I get a negative value for the magnetic field. So it would look this way, symmetrically with respect to the origin, negative 1/2 of mu 0 j. We see that across that sheet of current, which is located at y equals 0, then we have a discontinuity of the magnetic field, delta B, which is the tangential magnetic field, that's the only one that exists, delta B equals mu 0 j. That should remind you what happens with electric fields. We have the same idea. When you have an electric field across, or measuring the electric field across a sheet of surface charge, we found that the difference between the two magnetic field was equal to sigma over epsilon 0. Whereas here we have mu 0 j. So these expressions are very similar, except that this is for the normal field. The field had only a normal component. And this is for the tangential component of the B field. So once again, we see similarities and differences between the two. Notice also that the magnetic field in this situation is completely uniform, 1/2 of mu 0j. We have no angular dependence and no distance dependence anymore. The field above an infinite sheet of current is uniform, both in direction and magnitude. All right, the interesting part is we can recalculate this magnetic field using Ampere's law. This is another very good practice for Ampere's law. So we're going to take this infinite charge distribution. I'm just going to make it as a thick straight line this way, going to infinity along the x-axis. I'm going to take my y-axis here, and we can try to, again, the current J, current density J is flowing out of the board, and we'd like to use Ampere's law to do that same calculation. So remember, to take Ampere's law, we take an Amperian loop, which here by symmetry, that loop is probably, the easiest loop is probably going to be a rectangular structure located symmetrically with respect to the sheet of current, and we're going to take it of a certain length L. And we're going to calculate the circulation of the magnetic field, or in other words, we're going to probe the value of the magnetic field along that circuit. Every element dl, we're going to measure the magnetic field and circulate that dl all around the circuit to eventually get to the total circulation of the magnetic field. So in other words, what we're doing is calculating the circulation on that closed circuit gamma, which is this gamma right here, of B dot dl. And we know that this is equal to mu 0 times I passing through that Amperian. So we're going to have two terms to calculate. First, the integral part as well as the total current passing through. It's not very difficult. All right, so we know by symmetry, first because we've done it before, but also by simple symmetry, we know that the magnetic field is going to be oriented in this direction above the charge distribution, or the current distribution, and in this direction below the distribution. So when we're going to circulate around this closed circuit, we're going to have to address the circulation along the top part, the bottom part, and along the sides. So finally, we can write this integral, this circulation, as the sum of three integrals. So we're going to have the path, let's call it to the top, of B dot dl, plus the integral along the bottom of B dot dl, plus the integral along the two sides, which I'm grouping into one, of B dot dl. So here's what we're going to have to estimate, and then this is going to be equal to mu 0 I through. Well, first tackle the easy one. The B dot dl on the sides. So on the sides, the magnetic field, remember, is still pointing this way. It doesn't change the magnitude nor its direction. So my dl, which by the way is oriented based on the right-hand rule, if you can see the current sticking out, then that requires turning the screw counterclockwise in order for the screw to come out in the same direction as the current. So that gives me my orientation dl counterclockwise. So we see that the B dot dl at every element along the sides of the circuit, B dot dl is going to be equal to 0 because everywhere B is going to be perpendicular to that element dl. So we know that this is null. We only have now to take care of this. Well, it's pretty easy because B and dl are in the same direction at the top, so this is integral B dl, and finally we're left with the integral of B dl by itself, which is dl. So we have dl at the top, and we have dl at the bottom. And this is equal to mu 0 I through. So 2bl equals mu 0 I through. So what happens to I through? This is going to be the total current that is flowing through the Amperian loop. And that's not very difficult to get because we know we have a current density of J. So this is simply mu 0 J times the length of my Amperian loop, which is L. What do we find? L cancels out across, and we find that B is equal to 1/2 of mu 0 J. Again, we find that same expression that we had found earlier through a more complicated calculation. But that more complicated calculation allowed us to calculate the magnetic field in the case where the current distribution was not infinite along the x-axis, remained finite along the x-axis. That gives you a little, an example of a little calculation, a little different than what we've seen in class. Another interesting calculation that is also relevant to other fields of engineering is to calculate what happens to a loop of current when plunged in the magnetic field. So imagine that you take a circular loop of current, and imagine that the current is going around in this loop. The loop has a radius of r, and it is plunged in an external magnetic field that is pointing into, yes, we're going to take it into the board, B. It is the B external plunging into the board. The current is constant, the magnetic field is constant. And we'd like to understand what is the, what is the situation, what is the forces that the loop may be subjected to in the presence of this magnetic field. Well, we can take a small element, dl of current. So we take a small element, here's my IDL, element of current, and look at what is the magnetic force, i.e. the Laplace force, acting on this element of current. Well, we have a current pointing this way, a magnetic field into the board, gives a force pointing down. That means we have an elemental force dFB, corresponding to that elemental length, radial in towards the center of the loop. Notice that every little element IDL will be subjected to the same force radial in everywhere. So the net force acting on this loop is equal to 0. But it doesn't mean that that we can just ignore this force. The net effect of all these forces is to try to compress the loop, make it reduce its radius. So it is building up tension, or compression rather, in the loop. And I would be interested in figuring out what is the force acting within the loop due to the magnetic forces trying to compress it, reduce it, its dimension. So it's a classic example of classic calculation that you'll see in physics or in engineering. How do we do this? Well, we take a small element, a sector of that loop. So I'm going to magnify it again just to see, and that sector is subtended to the center by an angle d theta. And we have a radius r. And that element of current, this is finally my IDL, highly magnified, is subjected to dFB pointing inwards there. So dFB is trying to bring this element of current in, but the rest of the loop that's sitting right there is holding back, assuming that the loop does not collapse on itself. So there must be other forces acting on it, and we can call these forces, call them T as if they were tension. It doesn't really matter what you call them. You have a force T that is opposing this tendency to bring it in, and that force T is constrained or confined within the rest of the loop. So the loop continues on, and the rest of the loop is holding this element of current and preventing it from collapsing. So how are we going to calculate T? This force within the loop that is capable of sustaining the pressure, the magnetic pressure. Well, we look at this element of current and establish Newton's first law, the stability of this element of current. So we need to look at what these angles are, because we're interested in what happens along the radial direction. Notice that along the x direction, or the horizontal direction in this drawing, the forces cancel each other. So what happens along the radial direction? Well, we have obviously FB pointing in, this element FB, and we have two tensions. So we should have dFB equals the projection of T onto the vertical axis. So we would have to know this component and this component of T, which of course are equal to each other. So this angle right here is actually d theta over 2. And you find it here because you recognize that the halfway of the sector is d theta over 2. So I have the same thing here, d theta over 2. You can look at it from the geometry, you'll find that this is d theta over 2. So I am interested in t sine d theta over 2, and I have two elements. So this is going to be 2t sine d theta over 2. This is the force, the two forces opposing the compression of the loop due to the magnetic field dFB. What is the value of dFB? Well, if there's a current I passing through an external magnetic field, dFB is equal to IB dl, the length of that. And that has to be equal to 2t sine d theta over 2. So how do we deal with that? Well, since we're working with infinitesimal, it's fairly easy to... So this d theta over 2 is going to be an extremely small angle, very close to 0. Sine of a very small angle is more or less equal to the angle when expressed in radians. So this is more or less equal to 2t d theta over 2. And this is on the other side, IB dl. Now we have a variable dl on the left side, a variable d theta on the right side. We can combine them together because dl, considering this is more or less equal to the following, dl will be a straight element, but this is more or less equal to r times d theta. So this is the connection, dl is equal to r d theta. dl is the arc length of radius r and subtended by an angle d theta. So we rewriting everything in the same expression, IB dl, which is r d theta, is equal to 2t d theta over 2. And notice that d theta cancels out. We don't even have an integral to be going. The 2 cancels out, and we're left directly with t equals IB r. Here's the amount of force that is present inside the loop due to the presence of the magnetic field. If you wanted to have the stress from a more material science perspective, or mechanics, the stress, which would be, in this situation, a force per unit length. The stress in general is a force per unit area, but here it's more of a unit length. Then you would divide T, you'd find stress sigma equals T divided by the length of the loop, which is of course 2 pi r. And you find that the stress therefore sigma is equal to IB divided by 2 pi. And that would be an expression in Newton per unit of length, Newton per meter. That would be the amount of stress that this loop would be subjected, the amount of magnetic stress in order to reinforce it, which is of course a mechanical stress applied to the structure of the loop. All right, let's switch gear a little bit and talk about Faraday's law, an application of Faraday's law. Now to rotational motion. We've talked a lot about linear motion, motional EMF from a linear perspective, and we said in class that this is also applicable to rotational motion. Well, let's see what we can do with it and verify that everything works fine. So we're going to take a rectangular loop, looking at kind of in a 3D structure. Here's a rectangular loop of side A and B. which can rotate along this axis parallel to its B length. So you have an ability to rotate along this axis. And this whole loop is punched inside a B field, which would be horizontal and uniform. Say we have a B field, a B external pointing this way through the loop. So it's kind of difficult to see again in 3D, so the easiest is to start to look at what happens from a cross-section perspective. So from a cross-section, here's the vertical, here's the horizontal, and imagine that I have a loop that's currently sitting this way at an angle theta with respect to the vertical. My B external is in this direction, and the loop is rotating at an angle at an angular velocity of omega. Let's get rid of that. Actually, I could have shown you how we're going to have to call it a different value. We're going to have an A, a B, a C, and a D. So what you're looking at sideways currently are the side A, D. And that's how we're going to correlate as we rotate that loop around this center of the loop, the origin. Oh. So let's look at what happens from a magnetic perspective. From the magnetic perspective, we have a changing in magnetic flux. Indeed, what happens as the loop rotates? So if you have rotation, theta is increasing. As theta is increasing, the cross-section area of the loop subjected to the magnetic field is collapsing, decreasing. The reason is because the area that's affected by the magnetic field is this section right here. This is the area finally that's affected by the magnetic field, and as the angle increases towards pi over 2, that cross-section area is decreasing. So we have a collapse of the magnetic flux. A change in magnetic flux means that we have induction phenomena. Induction phenomena as per Faraday's law. What happens? So the magnetic field is collapsing. The circuit responds in such a way as to oppose the decrease in magnetic flux. That means that there must be a magnetic field induced, B induced, that is trying to support the magnetic flux. That means a B induced must be parallel in the same direction as the external. So this requires a B induced, which has of course to be perpendicular to the loop in this direction. And then what is the direction of the I induced? The induced current that's responsible for generating that current. Well, it's easy to see that if you have a current running from A to B, curling into the loop, makes the current going from A to D. So in this configuration, we have an I induced going this way into the loop, so that would be a counterclockwise direction for the current as it circulates into the loop. So this was the beginning of the rotation. Let's see what happens as we continue to rotate the loop. So we're going to now take the loop, having rotated a little bit beyond pi over 2. Now the loop is oriented in this direction. Point A has dropped below, and point D is starting to lift up. My angle theta is oriented this way. So we still have the external magnetic field pointing this way, B external. So what happens to the magnetic flux? Phi B in this configuration. Well, now the area of the loop, the area that the loop presents to the external magnetic field, increases as the loop continues to rotate. So now we have an increasing magnetic flux. Change in magnetic flux, Faraday's law tells us that we have induction phenomena in such a way that the B induced now is opposing the increase in magnetic flux. So we must have a B induced whose general direction is opposing the B external. I must have a B induced pointing in this direction. If I have a B induced pointing in this direction, that requires a current going from A to D. Look at from the right hand. So we have, again, an induced current, which has not changed compared to the top part. I still have an I induced going counterclockwise in the loop, or more easily to identification from A to D. So despite the fact that we have changing the change in we have a change in the change of the magnetic flux, we still have the same direction of the induced current. So we can continue on with this analysis and go look at, as we continue to rotate the frame, now taking it in the configuration where the frame now is past pi over 2. The frame is oriented this way. My point A is down below, and the point D is in here. External magnetic field is still pointing to the right. So what do we have? We have now the area of the loop subjected to the magnetic field as the loop rotates. So here's my angle theta, rotates this way. The loop sees less and less of the external magnetic field. That means that we have a magnetic flux, phi m, or phi b rather here, is collapsing. Change in magnetic flux, Faraday tells us that there's induction phenomena. As there's induction phenomena, the circuit responds in a magnetic way in order to oppose the increase in magnetic flux. The induced magnetic field has to be pointing opposite. So we have a decrease in magnetic flux. The circuit responds such that the induced magnetic field is supporting the external magnetic field, creating a magnetic field pointing in this direction. So if you have a B field pointing in this direction, now that requires a current going from D to A. The current now has switched. Compared to A to D, but now we have a current going from D to A. So we have I induced goes from D to A. So the passage on the vertical of the frame is what triggers the change in the direction of the induced current. And then the last little element, the last quadrant that we can look at is to have the magnetic field, the loop, having rotated this way, A coming back up, D now sinking back in, with now the angle theta corresponding to this very big angle. B external is pointing this way. We now have the area that the loop presents to the external field increases, so now we're in a situation where your magnetic flux, phi B, is increasing. Change in magnetic flux, Faraday's law tells us that we have induction phenomena in such a way that the magnetic effect opposes the increase in magnetic flux. So there must be an induced magnetic field that is kind of a direction more or less here, with a component opposing the external magnetic field. This requires, of course, an induced current going from D to A in order for the right angle to work properly. So here's my I induced from D to A. And of course now, as soon as the frame passes back through the vertical, we get back into this configuration, the current switches again. So we have two switches of the current that happen when the frame is vertical at the point, which is very interesting. It's a point where the flux is maximum, where we have the maximum magnetic flux passing through the circuit, and that's a point where the current switches direction. So how we can calculate from a quantitative perspective these changes? Well, we simply apply Faraday Lenz's law. And Faraday Lenz's law tells us that the induced EMF is equal to the negative of d phi b over dt. So now we need to figure out what is phi b, the magnetic flux through the loop. Well, it's going to be the product of B dot A, the product of the magnetic field, the dot product of the magnetic field with the area of the loop. The area of the loop is AB, and the dot product brings me a formula AB cosine theta, theta being the angle at which the loop is rotating. Of course, AB, A is little b, big B cosine theta. So we need to calculate this as the derivative as a function of time. The loop is rotating with an angular velocity of omega. So we can relate theta to omega. We can say that theta is equal to omega t. This is an angular velocity. This is radians per second times time gives me radians. Here it is. The unit is correct. So we get phi b equals A, B, big B cosine omega t. We get the E induced, the induced EMF in a circuit equals the negative of the derivative, so negative ABB, and the derivative brings an omega, a sine omega t, and the derivative of cosine being negative sine, which creates a positive value right here. Of course, the induced current, I induced, is given by Ohm's law. E induced divided by R, the electric resistance in the circuit. And we get the I induced equals ABB omega divided by R sine omega t. Here's the induced current. It can be also expressed as a function of the frequency of rotation, because we get the frequency f, which is going to be expressed in hertz as omega divided by 2 pi. Once again, verify the units. This is in radians per second, and I divide this by radians. Cancel that. I'm left with 1 over seconds, which is indeed the unit of hertz for the frequency. So you can replace that if hertz is the frequency, the time frequency was the given formula. What is really interesting is to start to plot the I induced as a function of time. In fact, we can also plot it as a function of theta because it's a little easier to see. So let's do it as a function of theta. So fundamentally, your I induced is also equal to A, B, big B, omega divided by R sine of theta. So obviously at theta equals 0, the current is equal to 0, and then it becomes maximum as pi over 2, and comes down. Pi over 2 becomes 0 at pi, and then of course it continues on for the full period. We're back to 2 pi over 0 right here. So we see that the current oscillates between a maximum value, I max, corresponds to sine omega t equals 1, to a I minimum, an opposite value of max, the I max. What is interesting is this point. The current is maximum when the loop is at 90 degrees compared to the origin. So that's a situation where the loop is horizontal. Here's the loop right here. Here's point A and D as the loop has rotated by 90 degrees compared to where we measured it originally. So this is the point where the current is maximum. You'd think that this probably doesn't really make sense. Why would the current be maximum when in fact there's no magnetic flux? Well, that's the idea of Faraday as well. The current is not dependent on the magnetic flux, but it is dependent on the change in the magnetic flux. So again, your current is 1 over R d phi m over dt. And the change in magnetic flux, which here is only related to a change in the surface area exposed to the magnetic field, is maximum at that point. A small change in angle is going to make a very large change in the amount of area that is going to be exposed to the magnetic field. Whereas when the loop is vertical, here, a small change in angle here, a small tilt of the loop d theta, is not going to have a lot of effect on the section of the loop experiencing the magnetic field. Again, here it would have a huge effect. It's from starting to zero becoming non-zero very rapidly. And because it is dependent on dphi over dm, this explains why the maximum happens at pi over 2 and not at 0 or at pi. Where in fact, where the loop is right here, there is fundamentally, this is a point where you have very little variation in the magnetic flux that provides to a current equals 0, dphi m over dt, almost 0 right at that top, instantaneously 0, corresponding to a current equals 0. So we can calculate also the power dissipated by Joule effect inside that loop as an additional little calculation. So the Joule power, we know that the Joule power P joules is equal to R I squared. So, and this is of course going to be the induced current. This is going to be equals to R A squared, B squared, big B squared, omega squared divided by R squared, and then sine squared of omega t. So the power will also fluctuate periodically based on the orientation of the loop. What is probably very interesting would be to calculate what is the average power Pj, average power dissipated. Well, of course we have this cancellation by that. All these terms are constant, so these are going to stay the same. A squared, B squared, big B squared, omega squared divided by R. And then we're going to have to calculate what is the average value over time of sine squared omega t. Well, you may already know that the average value of the sine squared or the cosine squared is 1/2. So that gives us an average power of a squared, b squared, big B squared, omega squared divided by 2r. Here's an average Joule power dissipated in the loop. To find this, the easiest way, this is a little trick, a little mathematical trick. You say that sine squared omega t plus cosine squared omega t is equal to 1. That, nobody will argue with you on this one. And then you're going to say, well, since sine and cosine are both periodic functions with the same period, then their average are going to be the same. So in other words, average of sine squared omega t is going to be equal to the average of cosine squared omega t when you take it over one period. Well, if they're equal to each other, you're left with 2 times the average of sine squared omega t is equal to 1. Gives you an average of sine omega squared equals 1/2. This is a little trick, easy, or you can go back to the full calculation based on the mathematics to calculate an average of a function, and you'll land on that as well. Last little exercise that we'll do, a little different again. We're going to take a disk of charge, a solid disk of charge. And we're going to make this disk of charge rotate around an axis z, passing through its center, a charge big Q, which we assume to have a uniform charge distribution, surface charge distribution, a uniform surface charge density or constant charge density sigma, of course Q divided by pi r squared, if r is the radius of the loop. And we're going to make this loop rotate. We're going to make it rotate at an angular velocity of omega. And we would like to calculate at this center of the loop, or I'm sorry, of this disk, assuming that we can be at the center of the disk, what is the magnetic field created by the rotation of that charged disk? So interesting problem, different than everything that we've done so far. So from a conceptual analysis, it makes sense that there is a magnetic field, because now we have charges uniformly distributed in motion with respect to a fixed frame of reference, which would be the point of observation. So this disk by itself, during its rotation, is going to produce a magnetic field. How do we calculate this magnetic field? Well, we know the magnet. So again, you have a charge distribution. You're going to have to break it down into elemental line of current, if you want to think of it this way. And of course, due to the symmetry, you're going to take a small ring of charge dq. And that small ring of charge dq is going to rotate around the axis of rotation and produce a magnetic field at the center of the ring. So if you take this charge dq going this way, pointing in this direction, rotating in this direction, gives a B field in the opposite direction to the z axis. So we expect to have a dB pointing in the back here. That will be the dB created by that ring of charge at its center. So if you go back to your class notes, we've calculated the magnetic field at the center of a loop of current. Now this is a loop of current because we have the charge dq rotating. So the center, at the center of this, the magnetic field is mu 0 I divided by 2 times r, r being the distance between the loop and the point of observation. You know, it's the little radius of the loop. So obviously we're going to have to relate dq and I, or di, that way. So what is dq? The elemental charge. Well, it's a charge held within a ring of surface area 2 pi r dr. There is a surface area of that very small ring, and then I need to multiply this by the charge density, sigma. That's going to give me the dq. What is this? dq is rotating with a certain period, t, through for full rotation of the disk. So what is the di? Well, we know that the current is a change in charge per unit of time. Unit of time is going to be the time it takes for one full rotation. So this is going to be equal to dq divided by t, t being the period of rotation of that wheel, which we can, of course, relate to omega, because we got t equals omega over 2 pi. So unit-wise, it does not work. This is t equals 2 pi over omega. Here we go. So we now have our connection. Di is going to be equal to dq 2 pi r dr sigma divided by 2 pi omega. The 2 pi cancels out, and we're left with an r sigma over omega r dr. So the elemental field dB created by that charge, by that line of current, you know, this charge rotating, is going to be simply mu 0 di over 2r. And we can therefore find mu 0 di is sigma over omega, so 2 omega, and I have an r dr divided by r. Of course, the r cancels out, which gives us a dB, very simply, equals mu 0 sigma divided by 2 omega dr. The integration is pretty straightforward. Of course, the magnetic field net is equal to mu 0 sigma over 2 omega, integrating dr between the center and r, which is equal to simply big R. And getting rid of sigma, replacing it by q over pi r squared, gives me a magnetic field B equals mu 0 q divided by 2 pi r squared omega times r. And of course, one of the r cancels out. And you're left with B equals mu 0 q divided by 2 pi omega r. Interesting little problem. This is the magnetic field created by this disk of charge, uniformly distributed, rotating at an omega, at an angular velocity of omega. Except that I have an issue with omega should have been brought up here. This should be sigma omega. 2 pi over omega, sigma omega. So that brings omega up here, omega here, and omega here, and mu 0 q omega over 2 pi r. Here we go. So a unit analysis would have verified that we get Tesla. I would have caught that omega being in the wrong place. This concludes this little set of examples and exercises for application to the magnetic field calculation, Ampere's law, and Gauss's law. Well, we didn't use Gauss's law, but certainly Ampere's law. Thank you.